Dames en heren, ladies and gentlemen, beste collega's, dear colleagues, I hereby formally open this session and welcome you all for the public defense of Danny Gasman. Danny has presented to the Faculty of Science a PhD thesis on the topic towards resolving planet formation in action with James Webb Space Telescope mid-infrared instrument in partial fulfillment of the requirements for obtaining the degree of PhD in science, astronomy, and astrophysics. So Danny, you have now 45 minutes to explain to the general public and to the colleagues the main results of your thesis. Then I'll introduce the jury members.
Okay, thank you everyone for coming, and also for the people who came from a little bit farther. I'm so happy that you're all here. So as was mentioned, I am now going to present my work, which is entitled Towards Resolving Planet Formation in Action with JWST MIRI, with a longer subtitle of In-Flight Calibration of MIRI MRS and its applications to the study of water in protoplanetary disks, which is a whole mouthful, but we're going to break it up into bits. We're going to start with figuring out what JWST actually is. So JWST stands for the James Webb Space Telescope, and you can see it over here. So you can see these nice golden mirrors and the sun shield, and it is now, of course, flying in space. So a couple quick facts about JWST. It was a big collaboration between 3 space agencies, so NASA for the US, ESA for Europe, and CSA for Canada. But there were also many, many institutions involved in its development. It has a 6.5 meter mirror, so it's quite large actually. It was a whole endeavor to get this all unfolded in space, because otherwise it didn't fit in a launcher. There are 4 scientific infrared instruments on board of the telescope, and it was launched on Christmas Day in 2021. So it's now been operational for several years, and quite successfully so. But this was after about 30 years of development. It took quite a while to finish this space mission and launch it. It costs $10 billion, and the efforts of thousands of people. And I think the main question is, that's a lot, but why? Why would we spend so much money on this thing? Well, it's studying a couple of topics. It really covers everything from early universe, young galaxies, to the galaxies that are a bit closer by, star and planet formation, but also exoplanets that are already more mature. So it's covering quite a wide range of topics. And it's doing so in the infrared. And we're quite interested in the infrared for several reasons. So for example, for the early universe, you might know if an ambulance drives by, at first this sound will sound a lot higher than when it leaves. And this is because of the Doppler effect. Light does the same thing. So these young galaxies are moving away from us, and its light will shift towards longer wavelengths. These longer wavelengths will reach the infrared, so we can study these very young systems a lot better if you look in infrared wavelengths, because the wavelengths are just longer. Furthermore, it's less affected by objects in between. So if there's some cold dust in between a star that you want to study and the telescope, you're less affected by this in the longer wavelengths, in the infrared range. And finally, there are quite a lot of interesting molecules that emit or absorb in the infrared. So for example, there's a lot of water lines, carbon dioxide, C2H2 is also shown here. These are very interesting, but there is also a problem with this, which is that they're also present in our own atmosphere. So you can see here, if we're looking with our little telescope from the ground up to the sky, there are a lot of, for example, carbon dioxide, but also water molecules in our atmosphere, which means that infrared light coming from space will be absorbed by these molecules. And there are very wide wavelength ranges in the infrared light that we just cannot see from the ground. And that's why we needed to go to space. And that's, of course, the James Webb Space Telescope. Now, there's one instrument in particular that we're going to focus on. So we'll start with part one, which is the in-flight calibration of the MIRI MRS. So, like I mentioned, there are 4 different instruments on the telescope for science purposes. Most of these, 3 of them, operate in light a little bit of light that we can see, but mostly in near-infrared wavelengths. So that is the shorter parts of infrared. And then MIRI, the mid-infrared instrument, which, as the name suggests, operates in a mid-infrared instead. So it covers longer wavelengths, and it's currently the only instrument that fully covers the 5 to 28 micron range at this moment. There's nothing else that we can use. MIRI has 4 different modes, so you can essentially just take a picture in different infrared filters. So you essentially just take a photograph. You can also take a photograph while blocking light from a central star, for example, by putting a mask in front of it. So this is almost the same thing, except now, for example, if you have a very faint source next to your bright star, such as a planet, you can isolate the light from the planet and block the light from the star. Another thing that you can do is look at an object and get a spectrum. So you'll just get essentially get all the little bits of wavelength dispersed, and you get a spectrum out, and you can see at each wavelength how bright is this object. And then finally, you can also do something with an integral field unit. And what this means is essentially you take a photo as well, but every single pixel in your photo will have a spectrum by itself. And this is the mode that we're focusing on, and it's called the medium resolution spectrometer, so the MRS. The way that the MRS works is that when light enters its instrument, it is split into 4 different wavelength channels using these wheels over here, as you can see. These different bits of the wavelength range are split into different spatial elements and then into its spectrum after they are reflected off of multiple components onto the detectors as well. So the way that these detectors function is that they have a layer in which they are responsive to specific wavelengths of photons. This layer has a voltage difference from the top to the bottom. And because of this voltage difference, there's a bit of an electric field. This means that if light comes in, generates a photoelectron, because it has a charge, and this field has a different charge, it is moved to the pixel. So these are our pixels here. And on the left, your signal will slowly go up as you are gathering these photoelectrons. Now, as you do so, this voltage difference slowly decreases. And therefore, this electric field becomes less strong, reaches less high. So if you generate a photoelectron higher up in this layer that's responsive to this, you will not be able to move this to the pixel, and it doesn't get absorbed. Which means that as you accumulate your signal, you slowly start to slope off. You effectively become less responsive. Ideally, you would want this straight line, but you get this slope instead. And if you were not to correct for this, if you were trying to calculate your signal, you would try to get a straight line through this curved line. You would essentially underestimate how much light you gathered. So that is something that is corrected for. But there's another thing that is important, which is that not every pixel will be illuminated equally. So if there's contrast between different parts on your detector, that means that, for example, above this pixel, this voltage difference has already changed, and you have become less responsive, but the pixel next to it may not have, which means that this one will not be attracted to the pixel it's meant to go to, but to its neighbor instead. And this is referred to as the brighter, fatter effect, because you essentially spread out your charge, and your signal becomes less sharp, essentially. And what it looks like if you look at the signal that you're receiving, instead of sloping off, you start to gather more and more signal from your neighbor as the central pixel goes up in signal. So if you then try to get a slope from that, you're overestimating how much light you gathered. So these are things that need to be fixed. There's another issue, which is fringing. So before you have even before this layer has detected the photon that's incoming, it doesn't necessarily get absorbed at first pass, which then means that it is free to scatter throughout the detector. After that, it might get absorbed, which means that you get a signal like this on your spectrum. So you get these large variations. And because the detectors consist of different layers, there are different ways that the light can scatter and interfere with each other, and therefore you get different components. So you have this shorter period, and then there's this longer period variation on top. So that's quite complex. What makes this complexity even worse is that because it depends on how the incoming light interferes with each other, it depends on exactly what the incoming light looks like, so the illumination that you are looking at. And what I mean by this is, for example, whether or not your illumination is resolved or unresolved. And when I say unresolved, I mean if you look up at the sky and you look at a star, to us it kind of looks like a dot, but it's actually a little bit broader than a dot. So the light that's incoming is reflected by an aperture of a limited size. So you will never get an infinite resolution in a single dot. It will always look like a function of whatever your mirror looks like. So you'll get a bit of a blob. But this is what we call unresolved, because we do not see what exactly the shape is of the object. We just know it's too small for us to see what it looks like. So that's what stars generally look like to us, but also other objects that are just very far away. So we get this kind of blob pattern with these nice kind of snowflake spikes around it, which is very distinct for the way that the James Webb mirrors look like. And if you take a cut through here and look at the intensity of this light, you get this over here. You get this little peak, and the width of this thing is a function of the wavelength divided by the diameter of the mirror. So what this means is that the larger your mirror, the better your spatial resolution, essentially. But this also means that to get the same spatial resolution for longer wavelengths, so for example, infrared light, you need a larger mirror compared to if you are looking at shorter wavelength light. So for example, the light that we can see. So that's important to remember. What's also important to remember is that the MIRI detectors do not sample this, which we call a PSF, the point spread function, very well. So we're essentially getting about 1.5 pixels per width of the point spread function. So if you look at these orange things and think that they are pixels, you can see that there are only like 2 pixels that are on this signal. So if you have small shifts in where this PSF lands, you get small shifts in what part of the PSF is actually sampled by your pixels. And this has an effect on the fringe pattern that you get out. So this is a bit of an overwhelming plot. But if we look here at this black dotted line that goes through every single part here, you can see a little bit of a wavy pattern. That's the fringe pattern if you were to just uniformly illuminate your detector. And then these colored lines are the fringe pattern from a PSF that's sampled slightly differently each time. And you can see that there's a significant difference between the uniform illumination and even these slight shifts in how you're sampling your PSF. So for example, your amplitudes might increase, but also your phase might change. And this makes it a very complex issue in how you can remove these from your signal. So there's a couple of ways that you could remove this, which one of these is a static fringe flat. So what you do is you look at somewhat uniform illumination and you extract what the fringe pattern looks like from there. And ideally, if you have another signal, which is also something that's more uniform or extended, and you divide it by this fringe pattern that you've extracted from the other source, you should fully remove your fringes. That would be the ideal case. But this is a static thing, and we already saw that for a point source, depending on how it lands, while it's very different from what this extended source looks like. So for example, you will get a larger amplitude, you get a phase shift, and if you then divide it by the same thing, you are still left with some fringes. So the second step that is also often applied is a residual fringe correction. And what this does is that based on the geometry of the detector, we have some idea of what the frequencies are that these fringes have. So what we do then is that we essentially try to fit sinusoids, so this kind of pattern of specific frequencies and specific amplitudes, to the signal that we got out with a residual to try and remove whatever was left. And this works quite well overall. So you usually are left with sub% level fringes, still some fringes though. But there is a bit of a downside to this. So for example, here, if we look at this plot, the red line and the black line look very similar. So the red line is where we did not apply a residual fringe correction, and the bottom is where we did apply a residual fringe correction, and these wiggles are signature from an actual molecule. So this is a signature from CO, and you can see that it does have a bit of a periodicity to it, which means that the residual fringe correction, which tries to fit periodic features in your spectrum, might try to remove some of this. So if we look then at a power spectrum, where we find individual frequencies and see if these frequencies are present in our signal. So on the x-axis, we have frequencies, and here the power. If there is a peak, that means that this specific frequency is present in our signal. Then if we look at the blue lines are the frequency spectrum of a CO feature. Then the black line is of our spectrum here, without applying a residual fringe correction, and then gray is when we do apply it. And what we can see is that, for example, here, there was a blue peak, which is part of the CO feature. This was present in our signal, but after applying the residual fringe correction, it's gone, right? This happens here as well, over here, and over here. And this is an example of an actual fringe being removed because there was a black peak, not a blue peak, and after applying the residual fringe correction, we remove it and we go to the gray signal. So the risk of running the residual fringe correction is that it might try to adjust your molecules, the way your molecules look like in your spectrum, a little bit. And this may seem very subtle, for example, over here, but it does make a difference if you're trying to fit what your emission looks like and what kind of properties you derive from this. So we want to find alternative ways of correcting for this. So what we did is that we know that this fringe pattern depends on the illumination. So if we reproduce this illumination, we should be able to also create this static fringe flat, which should not try to fit your molecules, but from a star. And then you will have one for your PSF specifically. Now we know that these small shifts on the detector really matter. So what we do is we scan a star around all the positions where we would expect someone to place a point source on your detector. This way, you will have a library of fringe flats, for example, that you can apply, and they should match the fringe pattern of your science observation. So what you do is you slightly shift your PSF along your detector, and you slightly change where the pixels sample it. And then you can reproduce the fringe pattern that you got. The additional advantage of this is that we now also sample really well what happens to the charge and the charge migration as we change the contrast on our detector. So what I showed at the start, where we had our signal curving off and the other side was going up, and we were overestimating our signal, we can try to fix that now as well. And the way that we do this is if we, again, take our regular nonlinearity ramp that we're showing here, and we try to correct this, we want a straight line, right? This is what we want. So the way that we do this is we fit a polynomial through this line and only extract the linear part. And that's this. And that will be our estimate of what reality should look like. What we do then is we divide this linear part by the observed part And then we can see what number do we need to multiply by to get this signal to here. So as we go up in signal, we can see that we need increasingly large numbers to multiply to go to this linear level. Now, if we look at this one, which was a ramp affected by charge migration, our neighboring pixel, if we were to apply the same correction factors, you would end up with this, right? Because we're multiplying with increasingly large numbers, which means that this signal would just go up. But we want something linear. We want something like this. So we do the same thing, except for this ramp specifically, we get a similar curve, and we apply that instead to get a linear version out instead. And by doing so, if we look at this plot, we can see that we linearize our ramps much better. So for what we're looking at here is that if our signal is linearized well, you want to be centered around 0, right? So the more all of these bars are centered around 0, the better we're doing. So if you don't take this into account, you actually get quite a wide spread, and you can tell that your signal is actually not consistent at all. But if we do apply this, our signal is the linearity is a lot more centered around 0. So most of our ramps now more consistently look like straight lines instead of curves, which means that if we fit a slope through this, we're actually getting a more accurate number out. And we can see this, for example, if we measure the width of our PSF, so essentially how sharp can we see our image. The dotted line is if we don't apply this correction, and if the blue line is if we do. And we get an up to 20% improvement in how wide your PSF looks, which is a big advantage if you're trying to look at faint objects next to stars. If your star is not blurring the signal, you can remove it much better. A second thing that we noticed is that fringes are also inherently contrast, right? It's this sinusoidal signal in your spectrum, which means that you will have a bright peak and a fainter trough right next to each other, which means that charge can spill here as well. And if we look at this plot, for example, we have 3 different lines. The green is if we don't correct for anything. The orange is if we assume all the illumination is uniform, and the blue is if we apply our custom correction. Then we take the slope from the start, the middle, and the end, which should show us an increasingly larger effect from charge migration. And if we then look up at the right, in the green, which is uncorrected, you can actually see that as we go up in signal, charge starts to spill into these troughs, and you essentially make your fringes less deep, right? If we then assume that this signal is uniform, you still see this effect. A bit less, but you still see it. And if we apply a custom correction, we get much more consistent fringes. And the reason that this is important is that if you want to use a reference object to divide out your fringes, you want them to look the same and consistent no matter your observation. So this is actually a lot easier to correct, even though the fringes are deeper, than, for example, this case, because you'll be consistent. And we actually notice this as well if we look at so essentially this is a measure of how strong the fringes are still in the spectrum. The lower the number, the better. We have the blue case, which is if we don't correct for fringes at all, and you can see that's kind of our baseline. Then the orange case is if we correct for fringes, but we assume that they're uniform fringes. And we already saw that those don't match for point sources, right? Then if we look at the green case, this is if we use our point source extracted flat, but we do not correct for charge migration. And then finally, the red is if we correct for everything. This over here was our original target. So this should be perfect removal because we're extracting fringes, dividing them out from the exact same object that we extracted them from. So this should be the lowest, and it is, and it's doing very well. But you can also see that correcting for the charge migration makes a huge difference. This is still for these objects that are different observations taken at different time. We still do a lot better if we apply both of these corrections, because the fringes are just more consistent. Now, this does still depend on how close you fall to the grid that we had, because we sampled this star in these positions, in these red dots. These are shown here as well in the black dots. And you can see that this object falls quite close. This one almost falls on top of one of our grid points. And that's when you do the best. So if you're in the exact same location, everything should look most consistent. So that's still a bit of a caveat that you need to be close to where we got our reference object in the first place. Now, what do we want to do with all of this? What we have now is a more consistent PSF. The broadening will be more consistent. The shape will be more consistent because we're correcting everything from the ground up. If you do so, you can have more stable fringe removal, but because we're doing these tiny little scans on our PSF, we also will have a much more well-sampled PSF. So for example, if you have a star and you have a little planet next to it, what it looks like if you just observe this with James Webb is this. And this is actually just the PSF shape. You don't see a companion, you don't see anything. So you need to remove the star. And this is already possible to quite a large degree. So for example, you can remove the star and then isolate a little planet, which is great. But we want to improve this even further by applying our corrections such that this can be consistently done for many more observations and such that we can detect fainter companions next to brighter stars. And the reason that we want to do this in particular is because we want to study the process of planet formation. And that brings me to the next part. So what we're going to talk about now is a little step in the planet formation process. So how do planets form? Everything starts with a molecular cloud of gas and small dust grains, and these will slowly start to form protostellar cores. So this is what you see over here. So these accumulate mass, they collapse upon themselves, and they form a protostar. A protostar is not a star yet. It's in here, it's actively accreting material and growing. And actually, because there's a big envelope of dust and gas around it, seeing the star or the protostar itself is quite difficult. So what you mainly see is this envelope of material. This material is being funneled into a disk shape in the middle and accreted onto the star. There's also some material flowing out, and that's the main thing that you can see. Eventually, this envelope disappears, and then you're left with a disk around a young stellar object, a pre-main sequence star. Also, again, not quite a star as we know it yet, like our sun. This disk consists, again, of gas and dust, and this is the material that will be used to form planets. So as this material accretes, you can form planets and eventually have a planetary system, like this, for example. This is the part that we're interested in. The protoplanetary disk, which is the disk around a very young star, is the part that we want to study. And there are a couple of processes that are important in these disks. So if we look at this disk here, like I said, the star is still actively accreting material. The material from the disk is falling onto the star. The star is also irradiating the disk, so it's heating up the material that's in these disks. And because of this, you get several sublimation fronts. The temperature is highest closer to the star and at the surface layers of the disk, so you get decreasing temperatures you move out. You also get decreasing temperatures the deeper you go into the disk. And because ices of specific species, so for example, CO2 ice and water ice, go into the gas form, so they sublimate at different temperatures. And because you have a temperature gradient, you get different sublimation fronts of different ice species at different distances from the star. Why is that important? Well, dust doesn't just stay stagnant where it is. So as time goes on, because of the drag with the gas, the dust will start to settle to the midplane and migrate inwards. So this dust that's carrying ices on it will slowly start to cross the different sublimation fronts and release the ices into the gas. So because you do so, you get a varying gas composition, also ice composition, as you move from the outer parts to the inner parts, because they're gradually releasing what they were carrying with them into the gas. Now, another thing that happens over time is that substructures might form within the disk. And if a substructure forms, it becomes probably a bit harder for the dust to actually move inside. So you get the pressure bump that's catching the dust here. You get a bit of a pileup, but it might not necessarily reach the inner disk. So in this way, you can isolate, we think somewhat, isolate the material in the outer disk and the inner disk and change the composition of the inner disk. And why do we care about the composition of the inner disk? That's the part we mainly see with James Webb. So you can observe disks in two different ways. You can look at them edge-on, which means that the light from the star scatters through the disk material, and you'll see a lot of absorption features because the material will absorb the light as it scatters through the disk before it reaches your telescope. So you can see ices, gas absorption, and that sort of thing. What I'm going to be talking about most is face-on. So if you look at a disk face-on, you see mostly emission. So you see emission features from gas, you'll see dust. You won't see your ices, at least not in the wavelength range that we're looking at. The different wavelength ranges cover different parts of the disk because there's different temperatures that you reach. So in the near infrared, so the other instruments of James Webb, see a bit of the star and the really inner parts of the disk usually. And an AU is essentially the distance from the sun to Earth. It's a standard unit. So that's really the inner parts. The mid-infrared, which is MIRI, sees the inner disk up to approximately the water snow line. So that's this region. And if you want to look further out, you need to go to far infrared wavelengths or even millimeter emission. And that's really the outer parts of the disk. This inner region is important because this is likely where terrestrial planets form. So planets like our Earth, planets like Mars, likely form in this denser inner region. So if we understand the composition of these regions, we might understand a little bit better how our planets formed and what processes were important here. So I said emission. What is emission? Well, something is wrong. The text won't be there, but I'll just speak my way through it. So atoms have electrons around them. And these electrons can absorb photons at very specific wavelengths. As they absorb the photons, they go into an excited state. And as they then decay back to the ground state, they'll emit a photon at a very specific wavelength. And these are specific energy levels because these electrons can only reach specific energies, so specific wavelengths. And you might be familiar with this if you've ever seen an absorption and emission spectrum from an atom. So for example, if we look at hydrogen, we see in emission, but also absorption, very specific frequencies or wavelengths at which it is able to emit a photon. And we can detect that. Now, there goes the text. For molecules, this is a little bit different. Molecules consist of multiple atoms, and the main thing that we're seeing, at least in our infrared wavelengths, is the movements of these molecules. That's the energies that we're seeing. So we can see the changes in energy because of the movement. So that can be vibration in our little water molecule that we see over here, but we also see the rotation of our water molecule. And these all have very specific signatures in our spectrum. And because of these specific signatures, we can also infer what the temperature is, how much of this specific molecule is present in this disk, and all sorts of other interesting things. Now, I already mentioned water. Most of this is going to be about water. So let's talk about when is water actually present in the region that we're seeing. So we have here our water snow line. So this is where the water ice sublimates into water gas. And we have our little ice here. And the dust will migrate inwards due to the drag with the gas, cross the snow line, and release the water ice into the gas form. Now, the star is also irradiating the disk, which means that it can start some chemical processes. So one of these is, for example, photodissociation. What this does is that it breaks up your molecule. So it destroys the bonds, and you get different molecules in smaller form, essentially. But it can also heat up the disk, which means that thermochemical reactions can happen. So it can react with other molecules or atoms to form other molecules. So for example, if we start with water, it can be destroyed because of photodissociation. This then forms OH, for example, NOH, can do two things. If the temperatures are high enough, it will again form water. So in the hotter parts of your disk, you would expect to see more water than other, for example, the other option, which is CO2. So if your temperatures are low enough, you'll end up with CO2 instead. So we get more carbon-based chemistry there. So this is a bit of a difference. But the main thing is that the thought is that this migration process is very important in bringing oxygen and especially water into the inner disk. So let's take our first example then of a disk and its emission. We'll start with the disk of SZ98. That's shown here. So this is not James Webb. James Webb is not able to actually resolve the disk shape, but ALMA, which is a different telescope, is. I won't go into much of the details of ALMA because that's a whole other story, but what you see here is essentially dust. So this is millimeter-sized dust. So the brighter it is, the more dust there is present. And the star is all the way here in the middle. And there are a couple of interesting things here. It's a relatively large dust disk, and it has several substructures, as you can see. There's some gaps, and there are some rings. So it means that there's some dust pileups. If we then look at the inner disk and we get our spectrum, we see this instead. This is what we see with James Webb. Because it's so small, we only see a point source, a PSF, and therefore we can only get a spectrum out, and that's all. So this is what it looks like. This is a pretty standard spectrum for a protoplanetary disk. We see here this nice dust feature. This is a nice silicate bump. We see some CO at the start. We see some carbon-bearing species here, HCN, and CO2 is this little thing. But mostly we see a lot of water. So all of these lines are not noise, they're water. They're actual emission features. And if we zoom in on this is going to get a little bit overwhelming. We see a lot of lines. So again, I mentioned here the CO. So the black line is our spectrum. Then here at the bottom, the different colors are fitted models of what the molecular emission looks like. So the blue is water, for example. And then the red line is if we sum all these models together, and then we fit to the black line. And what we see, for example, what's interesting is that this is our HCN feature, this is our CO2, this is a missing acetylene feature, which is also strange because most disks do have this, at least noticeably. And mostly, the water is more overwhelming. So that's a bit of an interesting case. So we tried to fit these different regions with a water model. And what we see is that we need increasingly low temperatures to fit this emission as we move outwards in our wavelengths. So here in this plot, you see the temperature on the y-axis and the emitting radius on the x-axis. You can kind of see this as a measure of how far away from the star we're seeing the emission. And you can see that we're really decreasing. So it appears that we are able to see different regions in the inner disk through the emission, despite not resolving our object. And I already mentioned that it's interesting that this object has so much water, and the reason is, like I mentioned, it has a very large dust disk, which might imply that not a lot of drift of dust has happened, which means that not a lot of ices have been brought into the inner disk, and therefore we might not expect as much water to be present. Then secondly, there's multiple rather deep gaps, which should, in principle, stop quite a bit of this dust from migrating inwards, and therefore you shouldn't get such a water-rich inner disk. So we would expect it to be more carbon-rich and water-poor. We're kind of seeing the opposite right now. So that's a bit of a mystery, and therefore we set out to see what is the influence of the dust disk structure on the emission. So these are the objects that we studied. We see that we have quite a range of what they look like. So you have here, for example, a relatively small disk. We have larger disks with a lot of structure. And we have these two, which are a bit of our outliers because they have rings over here, then a really big, somewhat empty gap, and a much fainter inner disk in the middle. They still have a bit of a disk there, though. And if we then look at our emission that we get from James Webb, we see all of them here, and they are quite varied. I mean, they all have a nice dust feature, but the emission, for example, from water gets quite a bit weaker as we look at different disks. And if we zoom in on it, we see here, for example, quite a variation in the acetylene, which is absent in some cases, and for example, quite strong relatively in others, and the same is true for our HCN here. Here we're looking at the water, and we also see quite some variation in what this looks like exactly. So we're trying to distinguish between different scenarios. And these different scenarios are that either substructures in the dust are able to fully trap the dust, and therefore the ices do not actually reach the inner disk. In this case, we would expect to see a water-poor disk quite quickly. The other option is that it's partially leaky. So some of the dust is able to reach the inner disk. And in this case, you would expect to have a somewhat water-rich inner disk for a much longer period of time, because the water ice is only very gradually reaching the inner disk. And there is quite a bit of an ice reservoir that is available to replenish everything. And then the final option is that it's fully leaky, everything's going through, and then you get a very water-rich disk as well, but for a bit of a shorter amount of time, because the migration goes so fast that after a couple million years, the ices are out, and you can't replenish it anymore. Now, if you want to specifically see these drift signatures in our spectrum, we want to specifically probably look at cold water. So here, we're looking at our water snow line, and we're going to see what the dust with the ice on top is going to do. So as it migrates inward, it will cross the snow line and release its ice into the gas. So we get our little water molecules in the gas phase. Then it might diffuse back across this snow line and freeze out again. And this, because of this continuous process, and if you have enough drift happening, you would expect this colder reservoir that's really in these colder regions where it's almost going to go back into ice. These would be stronger compared to your warmer water lines in your spectrum. That's the expectation. And then if we look at a few of our disks, I took a few examples here. We have CI tau at the top and SZ98 again at the bottom. And here we have their radial profile. So this is essentially the strength of the dust from the middle outward, right? Focus on the black and the gray line. So they both have a bit of a dust pileup, quite relatively close to the star. SZ98 has this as well. And they're somewhat larger dust disks. So you could imagine that they're somewhat similar, but their emission looks a bit different. So what we're going to focus on is these specific water lines. Because if we look, the hot water is the red. If the water is a bit warmer, you get this light blue. And if it's very cold, you should see these two lines over here in this quadruplet the most. They should be strongest compared to the other water, right? And that would mean, presumably, that most of the drift is happening there. So then if we look at CI tau, we actually see that this is quite flat, right? This is all normalized. So don't look at the absolute strength, look at the relative strength between the lines. And because it's relatively flat, the emission is probably quite dominated by quite warm water. So you wouldn't expect this disk to have a lot of drift happening. And that makes sense, thinking that it has substructure, it's quite large. So in this case, there might not be that much dust reaching the inner disk. However, for SZ98, this is a bit different because it clearly has very strong lines that should be dominated by cold water. So then, if it also has a deep substructure and it's quite large, why is there still dust going inwards? And this gets even more extreme if you look at SY-Cha, which has this huge deep gap, which you would think would be able to stop most of the dust, but you see a similar signature. So then the question is, does transport happen past the gaps? Are we thinking in two extreme terms when we're thinking of the transport? Or is cold water even a good drift tracer? Is the strength of these lines even a good indicator of what's actually happening at the snow line? Are other mechanisms more important in driving this emission? Or are the gaps just inefficient at stopping the transport? They just don't. That's also an option. So what is actually happening in the gaps? And why are we interested in what's happening in the gaps? Well, one of the reasons is that gaps could be formed because of planets. So within these gaps, there might be a little protoplanet, little baby planet that is forming. And this planet is forming For example, by gathering the material around it. So the material that it's gathering, we should understand what the composition is and what's happening there. And if we zoom in on this little planet, we can even see that it creates its own little disk. And this little disk is the material that it's directly accreting, but it's also the material that is available to, for example, form moons. And by applying our corrections from part 1, where we should be able to do better at removing our bright star and get a little companion out, we might be able to study this disk and this process a little bit better. So to conclude, from part 1, previous work did not account for the impact of the brighter fatter effect, even though it's very significant. BFE also impacts fringing, which I think is most important because there's a lot of groups that are taking references to divide out their fringes. But if you have a large difference in how bright your illumination was, you might get a difference in your fringe pattern and it won't work as well. So you need to correct this before you correct fringes. And up next, we will use these results to improve high contrast imaging. That's what I mentioned last. And from part 2, we know that these gaps might not be that driving in stopping some of the dust drift, or other processes are just more important in what we see in our spectrum. And finally, we can apply the improvements from part 1 to hopefully study the planet formation process a little bit more directly. And that's everything I had, so thank you. That you should be taking care. Yes, and then it's a microphone for you. Wait, does it work? Sorry, should I?
Thank you very much. All right. Thank you very much for your presentation. Before we move to the discussion, let me introduce the examination members. So let's start with the 2 people online. David Lowe in the US from the Space Telescope Science Institute, and Inga Kam from the University of Groningen. So thank you for joining. Then we have several members from the KU Leuven, Joris van de Wondel, professor in astrophysics department, Pierre Royer, Bart van den Busche. We have 2 PhD supervisors, Yanis Arigiru and Denis Defrère. For the private defense, there was an extra member, Ewin van Dishoek from Leiden Observatory, but she cannot join today. And I'm Olivier Namur from the Department of Earth Sciences. So I will start by asking Inga Kam, if she wants to ask some questions.
Well, thank you very much. First of all, also thank you very much, Dani, for this wonderful presentation of your work. I have to say I was very impressed when I was reading your thesis because, as you know, I've been very involved in the MIRI instrument as well as in setting up the disk observational program. And so actually your work is almost like a synthesis of my dreams. And I think you've been very, very crucial in pushing for the calibration and getting the best data quality out, as well as actually harvesting some of the crucial science that we had set out to do. So again, you know, my compliments for a great thesis. I have actually 2 questions, and I would like to start with one, which is maybe a little bit more technical. You embarked on this method to use the power spectrum actually to show where the fringes live, to show where the CO molecule lives. And as you know, there are still a lot of little wiggles and things we have not identified yet. And so since the CO molecule leaves a very clear imprint in the power spectrum, I was just wondering, you know, whether you could see the power spectrum method as a viable pathway forward to maybe even look for molecules that we haven't identified yet. I mean, maybe they are caught in the little, you know, weak signals, and maybe we could do something better there, like looking at ammonia or, you know, SO2, one of my favorite ones to search for. So do you think the power spectrum method would be a good approach here?
If the periodicities are sufficiently different from what we expect from the fringing, I think it could be possible to isolate this a lot better. Of course, this is dependent on how well you know your molecule and if you have a good spectrum of it so that you know exactly where it's meant to be in the power spectrum. I'm also not sure if the specific emission that you might get, depending on the temperature and the density, if that might change some things in the power spectrum. I'm not sure if that would adjust things significantly, because in that case, you might also want to have multiple models at different temperatures and compare and see if that matches. I'm unsure how well that might work if there's a lot of overlap in the power from different molecules. Maybe if you know exactly where they are in the spectrum and they are sufficiently separated, and then you take the power spectrum from that part of the spectrum only, that might be a bit better. But yeah, I think it could be possible, but I think you would really need to know your molecule quite well. But to be fair, that's also true for identifying them in your spectrum to begin with.
Yeah. Okay.
I need to think about that more. Yes, thank you.
Well, maybe we can find some new clever ways to at least find the molecules we were expecting, but we didn't see it.
Yeah, for sure. That's it's a bit of a mystery there.
Well, and I do have a second question, which is more pertaining to the disk part itself. So I don't know, I have your thesis open here, and for me it is figure 9.3 in the thesis, but I don't know if that is relevant. But if
I don't have my thesis in front of me.
No, but I would describe I
Okay.
would describe it to you. So it's largely where, the last part of your presentation as well, where you looked at the line ratios, for example, of cold to warm water, or the cold water intensity with respect to the, normalized to the accretion luminosity as a function of the dust gap size, or where the dust cavity is. And I found it very intriguing that, there is a kind of tentative relation. If you have a very small dust cavity, you see a higher amount of this cold over warm water, and then as you go to larger cavity sizes, actually it seems to go down. However,
sorry, I think the plot is for the dust disk size, right? Not the cavity size.
Yeah. Oh, sorry, it's the dust disk size.
Yeah.
Yes.
Yeah.
But what was very intriguing actually is for the large disks, the data itself, so that ratio is all over the place, in fact.
Yes. Yeah.
But for the small disks, it's much more confined. It's much closer to the kind of tentative relation that you draw. And I was just wondering if you could tell us a little bit more about why you think that is the case. Why do we see a huge diversity in this ratio for the larger disks? And why does it seem to be much, much more tight and, closer to each other for small disks?
Yeah, I think there's two possibilities here. One is that I actually don't include that many small disks because I only included the ones where we know that there are substructures. And that's actually not yet that well known for a lot of the small disks in our sample, simply because of limitations with the resolution that they've been observed with in ALMA. So I think one thing could just be bias in our sample, that we just don't have enough small disks to see this. I think the second option is that these small disks imply, I think, that if they do imply that the dust migration process has gone more smoothly, then it makes sense that for them it's more consistent. But in the larger disks, there might be a huge variation in what the depth of the gap is, what's causing this gap, is it actually preventing dust drift? And there, I think, because we are not exactly sure to what extent this is all happening, I think that's why there's a lot more variation there. It seems that for the smaller disks, clearly something has moved inwards. So maybe that's why that's a bit more consistent. But I also think it could very well just be a selection bias right now.
Okay. So we need to get more disks into our samples.
We need more ALMA disks.
Yeah.
We need to know if they have substructures.
We need more ALMA data in a sense. Yeah.
Yes.
So that is maybe. Do I still have time for one last question?
Yeah, please go ahead.
Okay, so my last question is along those lines, actually. So we still see, there are some trends, there are some ideas in the JWST data, but, as you also show in your thesis, there's still a lot we do not understand. So looking a little bit into the future, I'm wondering, from your point of view, what kind of ancillary data do you think we need to get now urgently for the inner disk to be able to break through some of the issues of our lack of understanding? Do you foresee that, it's more urgent to get like imaging of the inner disk, and then at which wavelengths? Do you think we need to get, spectrally resolved spectra, so higher resolution spectra, at which wavelengths, etc.? So I'm just curious to hear what you think. How can we break through this kind of still existing model and interpretation degeneracies?
I think there are two things to me that stand out the most, which is that there's in models that are pointing towards this drift story being very important and substructures stopping this, there's the assumption, I believe, that most of the ices, first of all, are quite neatly layered, and they're also predominantly brought inwards on larger dust grains. And larger dust grains are, of course, a little bit easier to stop. With smaller dust grains might still carry quite a significant part of these ices. So I think one thing is more edge on disks and understanding a bit better what the ice composition actually is. Of course, far infrared can be interesting as well for studying the ice composition, but that is currently far in the future and perhaps not even happening, so we'll see. And I think the other thing is to study whether these gaps are actually deep enough. So looking at the gas, for example, might give an indication of whether these gaps just exist in the dust and there's quite a significant amount of gas still present, which could still carry in quite a bit of the smaller dust grains. So CO isotopologues with ALMA would be nice.
Okay, well, let's push that message to the TAC. Thank you very much.
I tried.
Okay, thank you very much, Inga. Now I will ask David Lowe if you want to ask some questions.
Good morning. Can you hear me okay? Okay, I'll take the nod I can just about see as a yes. So first is the MOS lead at Space Telescope for many years. Let me both thank you for your presentation and also for the effort that you've put into the calibration of the MIRI MOS over the years. It's been a pleasure working with you on all of that, and it's really something that bears noting that the efforts that you've put in have helped improve MOS science far beyond the realm of planet formation that you've been talking about today, and going all the way from the nearby solar system out to observations in the distant universe as well. So thank you for all of your work. A couple quick questions for you. For a lot of the presentation where you were discussing the calibration work that you've done on correcting the bright fatter effect, the issues with fringing, etc., then you've been using observations of the bright O star 10 Lacerti. Can you comment a little bit on why that was a good target for this work and what some of the drawbacks of using that target were?
So the reason we thought it was a great target is because it's quite bright. So our problem is that we're working in the infrared, and calibration stars that we know quite well are actually not that bright in infrared. But this one is relatively bright, so it still had quite a bit of signal in infrared in the MIRI wavelength. So that was very nice. Of course, we then found out through your work as well that actually this isn't a very well-behaved calibration star because it has very broad emission lines. Oops. So that's a downside because we needed to remove quite some chunks of the spectrum to not have these emission lines propagate into a science observation. Another downside is also that I mentioned it is still a star. So in the very longest wavelength, so longwards of about 20 micron, it still becomes too faint. So either we observe this thing a little bit longer, which is a bit inefficient, I think. We might want to look towards redder targets instead. But for the shorter wavelengths, I think it was a pretty great target still.
Okay. And for the actual BFE correction itself, then that's a series of linearity corrections based on polynomials that you've derived as a function of the distance from the star. But how well do you think that might translate translate to more complex scenes where you have, say, multiple sources in a scene at a given time, and you have to start worrying about, distance from multiple things producing a competing effect on the detector.
Yeah.
Here I'm thinking as well about things that aren't necessarily real sources, but are detector artifacts. You have to worry about things like unmasked cosmic rays, bad pixels, or etc.
Yeah. The cosmic rays and bad pixels, I think, they behave so differently. I don't think that you can use a standard correction for that, especially for cosmic rays, because the energy is different. I think that requires a different approach. But just to go for nonlinearity and BFE combined for more extended targets or binaries or what have you, you can, which is what I did briefly look into but never really finished, was the deconvolution of the data. So if you get the correlations between ramps, because for BFE, they are correlated between pixels up the ramp and with their neighbors. But for linearity, it's only a function up the ramp. So in this way, you can get, through these correlations, you can understand to what extent these things are coupled, and then deconvolve them, which I know that you've maybe seen that Jeroen tried this a little bit, but we need to characterize our detectors a little bit better to get this to work. So for example, flat fields would be great, very long exposures and multiple. Another approach that we've been thinking about is using my data for 10 lakh, taking the nonlinearity correction that I have with the charge migration correction, assuming that this is actually truth, and deriving all of our variables from there, such that we can derive a deconvolution kernel. So that is something that we've been thinking about and discussing, and I think that would be the best way forward, because in that way, you're not dependent on knowing what your illumination looks like, because otherwise you might want to fit things to the detector, figure out, is that a star, what's happening there, how bright is it, so that you can predict what your ramps look like. In this way, you can just do it more coherently. Does that answer your question?
Okay, thanks. And that actually kind of starts to get at one of the next things I was planning on asking, which is that a lot of the analysis that's been done so far by many people starts with the data cube space, where you've moved away from all of the detector level effects. And I know that you're interested in kind of trying to get back closer to the raw data itself so that you can go beyond what we've been able to do so far. I was wondering if you can comment a little bit on what you see as some of the remaining tall poles for that work, whether or not you can get a factor of X by going back to the detector, how much you then need to worry about other detector effects, and things like cosmic ray showers might be limiting factors if you're looking at faint companions, and etc.
Yeah, so, well, I think one of the advantages of looking at the detector is that the cosmic ray showers are actually quite clear when you look in the detector space compared to cube space. So one of the things that we could do is, if we know our PSF very well, we can actually do a little bit of an outlier rejection on the detector already and remove our cosmic rays in that way. So that's one advantage there. In terms of improvements in general, I don't know the exact percentage, because the work that has been done before us on this topic extracted spectra from just summing the full detector per wavelength, of course. But that's not what we're doing in the pipeline currently. We're taking an aperture. So I'm expecting the improvements to be lesser, because they quoted 30% improvement in SNR for the same observation, which is, of course, quite huge. I think it will be a bit less, but I do still think that we might. I can't put a number on it, unfortunately, but I do think we'll see an improvement. As for other detector effects, of course, we'll still be limited by persistence and reset anomalies in RSCD, which is, I don't think we have the data to fix because it's so variable. So I'm not sure how much that would affect things. But I still would just say add an extra reset. We've had that discussion.
Okay, thank you. I guess that kind of takes me into the final thing I wanted to ask, which is that you've been working on trying to tease data out of the MOS observations for a number of years now. But if you could go back and change one thing about the MOS hardware design, what do you think the ideal thing to change would be?
The ideal thing to change, I mean, if we have more up-to-date detectors, something, but That's of course difficult because at the time this was the best thing that we had, I think. I know that now we're going more towards photon counting with the kit detectors. Something like that would of course be better because then you won't have fringing. I don't know what's going to happen to charge migration because I'm not too familiar with their hardware. But yeah, just a higher quantum efficiency would be nice to prevent scattering. Another thing, I don't know what happened to our dichroic wheel, but if we could just not have that happen, it would be nice.
That'd be fantastic.
Yeah, I don't know what the problem was, but you know. Yeah, and I think that's it for the top of my head.
Okay, thank you.
Okay, thank you very much. Let's now move on to members from the K11, and I'll ask with Joris van de Van.
Okay, thank you, Mr. Chairman. So first of all, Danny, congratulations. I think one of the things I said was for me as an outsider, just already to comment to the public, not in the topic at all. I think this presentation was really nice compared, let's say there was an added value as you as a teacher, for me at least.
Okay.
For the rest, your family will, at least I think some of them will
tell
feel
me.
the same. You did a really nice job. First thing, also, I think I have to congratulate you. You did a lot of hard work. And so I will give this book to my group for two things. I mean, for the hard work, for sure. But then if I see on slide 2 that the James Webb Telescope is also during Christmas launched, I have the feeling this is a very hard-working community. And also it's a beautiful cover. But so then I had actually the same question as the last. What would you do if you go back in time and say, look, I'm in the meeting, I know what has to be done, but then let's trigger it, let's continue on that. Can you comment for me as a non-expert, what is the temperature in the James Webb Telescope? And of course, I can imagine, but treat me really as a non-expert, that the temperature will depend on where you're looking at, so which direction you're pointing, and how this impacts your results.
Yeah.
And then, okay, let's start with that.
Yeah. So the overall temperature is, I believe, around 30 Kelvin for most of it. But of course, MIRI is cooled because it's mid-infrared, so you really need to cool it down significantly to not just see your thermal background. So that's around 6 Kelvin. And it's quite stable from as far as I'm aware, because you're actually you're facing the same, you're blocking the light from the sun, earth, moon at the same time at all times. So I think in terms of variations, it's quite small. I believe the largest variations that we're seeing if we're switching modes, for example. So if we change our detector readout, there's a bit of a shift in what's happening to the temperature. And you can see a signal of this on your detector as well. And especially in the longer wavelengths, the background just shoots up. So you really need to, you will even see fringes in the background, essentially. That's how it's quite bright. So yeah, that was your question.
And that's
right?
taken into account in the model, because there are already a lot of, let's say, ingredients, but let's say in the fitting, this is taken into account, the temperature?
No, the fitting of
let's
what?
say if I don't know,
Yeah.
They have a temperature
yeah.
sensor and they say, okay, temperature, this is an input in the model, or it's completely, so
No,
it's just
not used at all.
Okay. And then let's, I have some time, let's say, related to the you mentioned kit detectors. And then I wanted to see my relevance to the topic in the future.
I shouldn't have mentioned them.
Yeah.
That's my mistake.
But indeed, because this is very traditional. Don't get me wrong, the James Webb is very involved, but it's at the end, it's a very long process. So from a condensed matter perspective, it's really old.
Yes, it is.
In essence, if you see the evolution. So can you comment, what are the next kit in town when you look to detectors? So, and then you see, will superconductivity really play a major role in this?
I would hope so. I would like to see that, because I think one of the problems that we're having, one of the issues with this is that because it's not as efficient at absorbing the photons at these wavelengths, we need quite thick detectors, and that's causing all sorts of issues. You're more susceptible to cosmic rays. The cosmic rays are doing weird things as well. They're scattering throughout, causing weird signals. So I think if you have more efficient detectors and you can make them thinner, that would be great already. Also towards more photon counting, a lot of these issues will just not happen, like fringing. So that would be nice. And yeah, like these detectors are from the 90s. And I think most of the improvements have been made for near IR detectors, but the mid-infrared has kind of been left behind from my understanding. So actually the near-infrared detectors that are being used for the other instruments are, I think, a bit better than what we have for MIRI. I think another issue was that it was never really meant, these detectors were never really meant to be operated at such a low temperature, which has caused a whole other range of unexpected effects. So yeah, no, developments in these kinds of things would be quite great. I'm not as familiar as I would like to become with some of these other techniques. So for example, the kinetic inductance detectors, that would be nice. I would like to learn a bit more in the future about these techniques as well.
Yeah. Okay, then if I may, let's go to slide 36. And again, treat me as ignorant.
I will see how fast I can get there.
It's about your explanation of, if I understood properly,
yeah.
Let's say you observe something and it doesn't fit the story of seeing the gap.
Mm-hmm.
But then my question is, and it could be completely stupid, but of course this is a picture at one moment in time.
Yes.
So it could also be an explanation. There was no gap, and then there was transfer, and now you see a gap and you see water. So is that also not an possible explanation?
Yeah, so that's actually one of the important things is the timing of these gaps. If they form early enough, yes, then they can influence your inner disk emission. If they form very late, and like you said, they formed and everything's already moved inwards, then yeah, they're not going to influence your emission as much or your inner disk composition. We have seen indications that they do form quite early on in the lifetime. So actually before the class 2 phase that we're looking at now. So if you go even younger, there are some hints that it happens somewhere between these two phases. We don't know for sure. This is a big uncertainty about when exactly these gaps form. But no, you're completely right. Variability could very well be an explanation for why things are different. That's actually one explanation that's been brought up for the emission SZ98. It could just be that it had an accretion outburst. What this does is you get this big heating up of the disk, your snow line moves outward, and suddenly you get a lot of extra water emission. And this could potentially persist for many years, even when the outburst has passed. So that is a potential explanation. Variability is definitely something that we need to look into next. And the time scales over which these gaps form is also uncertain and should be more certain if we can make it so. Yes.
Okay. Last final question then. I give experimental basic skills, no? And then there is it fits to some extent. So I'm wondering, what you have to do is you have to increase the signal to noise ratio in a good experiment. In electronics, we can do that. For example, you have a 50 hertz signal, you don't want that. So you use a band stop filter because you can build this very easily. Obviously, this is much more complex here to build filters for the. So my question is, did you also, if I understood, there is regions where there's a lot of noise in the frequency spectrum. So can you not just simply identify the best spots to measure and really look like there are the molecules? So instead of always looking to the full target, what I would say is you first do the frequency sensing of your device, and then you find gaps where there is less noise, and you really trigger that regions to do your exploration, or that's an impossible.
Are you trying
So what
to...
I mean is, no, sorry, what I mean is to be simple, is you have the
Yeah.
physics, it happens at a certain frequency, molecules
Yes.
in this
Yeah,
case.
yeah.
You have the noise,
Yeah.
if you want a region where there is no noise in that frequency region, but where is there physics? So can you not like identify bands of better...
I'm sure you could, but it's a bit late now, I think. I mean, the signal is just dispersed across the detector downwards. You can't adjust where exactly your specific wavelength is going to fall on your detector. So if you're lucky, and for example, one part of the detector is less noisy, and that happens to be where your molecule is located, that's great. But you can't influence this. If I understand your question correctly, I don't think this is something that right now we could change.
Okay, yeah, but I think that's, for me, in the lab, it's very easy to change the
Yeah.
knobs.
I mean, if you want to become an astronaut, this could be the moment.
Okay, I'm going to change it. Okay, thank you.
Okay, Danny. So yeah, congratulations. Indeed, I had great pleasure in reading your work, which is very impressive, by touching the instrument part and the scientific part. And I would join Joris in congratulating you for the presentation in which you brought a number of, concepts which are not so easy to bring in a very clear way and very structured. So very, very remarkable presentation. Thank you. So for the question also, I would partly join Inga and Joris in asking about the cold versus warm water. In your work, and I think also on slide 38, you present the two targets with large gaps as outliers, so PDS 70 and SY chameleon. But here you show that actually SZ 98 and SY chameleon behave the same in terms of water ratio. And also in this figure 9.3 that Inga referred to, where Inga saw points all over the place, my eye saw more two groups,
yeah,
like high ratio and low ratio, yeah, where indeed the two sources with a huge gap do not appear as outliers. And so it's more like SZ98 and another source which are joined. And so I was wondering, and this goes along with what the question you have on the next slide, which is, are there other mechanisms at work? And so the question from Joris was also like, could age play a role, or could there be, what could be, if these groups with more targets would prove to exist, mm-hmm, what could be the driving parameter for such a distinction between these groups?
Yeah, age is indeed very important, aside from when the gaps form. If your star is older, then some of these processes have already happened. Unfortunately, we don't have very clear age estimates. So like the range on these things can go from, oh, it's 0.8 million years old, but it could also be 15 million years old, and we don't really know. So the age estimates are quite broad, and this is a problem for most of these objects. It's a bit difficult to determine. So unfortunately, I tried to see if there was some trend with age, but it's difficult to see because of the error bars. So that wasn't possible at this time, but that could definitely play a role. I agree. Another thing that I didn't mention in my presentation, but we're comparing cold and warm and hot water. But you know, the material close to this star is quite faint. It has a gap between the star and the actual disk. So that means that your water is just colder. You will just have more colder water compared to warmer water because there isn't any material close to your star. And that's another thing that could be influencing why SYCHA and PDS 70, which are both going towards being transition disks where the gas is being removed and you would only have debris left, they're in this transition phase. So it could very well be that the reason there's less warm water compared to cold water isn't because there's more cold water, it's just because there's less warm water. So that's a bit of it's one of the reasons why I'm not exactly sure if this measure is a good measure. This might not directly indicate or say anything about drift specifically, because there's a lot of things that could influence this. Like I said as well, the accretion outburst where you're heating up your disk all of a sudden, that's now also brought up as a reason for how you could have more colder water as well. So none of these things are drift related. So that's a bit of a thing.
Okay, thanks. Then if I may, I will move to completely to the introduction, from the very end of the thesis to the introduction.
Okay.
I have a question which is a very small detail that you present well, in your presentation you insisted on the fact that an accurate knowledge of the pointing of the spacecraft is really crucial. And you present the histogram of the pointing error, and that histogram peaks at values which are much smaller than even 1/10 of a pixel of MIRI. So I guess it's not derived from MIRI data. So do you know where?
No, I think this is David did these measurements.
Okay.
So he can nod if I'm saying the right thing. I believe these are from MIRI data because you can't do this. So these are the pointing. So the pointing accuracy of the telescope itself is very accurate, much more accurate than what we're measuring with MIRI. All right.
Yeah.
So with MIRI, we're seeing this broader spread. So this is measured from MIRI data, and I think specifically also MRS, because you're trying to compare to where am I expecting this thing to land and where did it actually land.
Okay.
And because one of the reasons we think that the pointing is less consistent within MIRI compared to the telescope itself is because of this lovely dichroic wheel that's not functioning as well as it should. So.
Okay, thank you. Yeah, that's it.
Bart. Yeah. Thank you, Danny, for the very nice presentation. Indeed, it was very clear. There are a couple of things I understand better, and you will notice that in one of my questions. It was, not only the thesis was nice to read, the presentation nice to listen to, but also just seeing your work in the last couple of years in the MIRI team and in the DISCS program was very pleasant to see. You were very often starting from an underselling position, not overestimating or putting things in a relative context and so on. But I think today we've seen that you're completely over this this phase, because the self-confidence that I've never seen anybody who dares to come to a PhD defense without bringing a thesis. So, but that's a first in my life. But then again, it's a very big thesis, so it's quite a heavy weight to carry. So I understand it fully. Now, on so your first part about the brighter fatter effect. You showed a very nice animation or cartoon showing what the brighter fatter effect, that it's about the charges who are moving to the neighboring pixels because of the local field, which is above the pixel, is different. But in your model that you show, or that you have derived in chapter 4 of the thesis you don't have with you, you do the fit in arc seconds on the sky. You fit the model for the brighter fatter effect for where the flux is away from the center of the observation in arc seconds on the sky. While in your beautiful cartoon, you show that this detector doesn't know about arc seconds in the sky. The detector knows about the pixels and about the charges and how big these where these charges go. It doesn't know about it. So is there a potential to improve your correction even better, not doing it in arc seconds in the sky, but in pixels?
So I don't think this is going to make a difference, because you can do it in pixels, you can do it in arc seconds. If the arc seconds are based on the local coordinates of the pixels. And you can either measure your offset, because it's dependent on how you're sampling your PSF. And the way you're sampling your PSF is defined by where do I think my PSF is and how far are these pixels away from the core of the PSF. You can do that in pixels, but I don't think this will make much of a difference compared to doing it in arc seconds, because it's just a coordinate shift. And of course, our coordinates aren't super accurate, but our measurement of where we're landing is most efficiently measured in arc seconds, I think, because the locations in pixels on the detector do not spatially coincide with what we're seeing on the sky. And also, one thing to add, there's 2 options for the corrections. There's the grid, where you actually you use exactly what that pixel measured in our reference, and you use that for your target. The interpolation is just if you're too far off from the grid. So that's for people who didn't listen very well to our advice, and then and you know, don't observe things as the most efficiently as you would like them to be observed.
Okay, but well, we disagree. But that's the beautiful thing about thesis defense, that you can disagree with among each other. But in figure 4.9 of the thesis you didn't bring, you show that. I mean, you're underselling things maybe a bit again, because you show a percentage of improvement as a function of wavelength. And my feeling is that if you would not try to do that in width of the PSF, that you or that you're making it narrower, but you just put it in pixel coordinates, which is more physically to the effect you're describing, your results could look better and flat and permanently.
But these results are from the grid based. So you're not actually measuring anything offset from your PSF. It's from the grid solution, which is just pixels.
Okay, let's try to
That's
find something
the-
we agree on, maybe. Do you, what
we
do you
can
think of
disagree
the term brighter, fatter effect? Is that an appropriate name for the effect? And isn't it time for the community to embrace a better name? And what would that be?
I think charge migration exactly defines what it is. Brighter, fatter is a bit of a misnomer because it says brighter is fatter, but just because something is brighter doesn't mean it's the only thing that can be affected by BFE. As long as you observe something long enough, if it's super faint, but you observe it for long enough, you will reach equally high up in your full well. You'll reach equally close to saturation, you will get the same BFE effect. So even though it's not a bright object. So I think charge migration would just be easier. We're not insulting anyone. And and it describes what it is.
Very good. I'm very happy we are starting to find common ground
Good.
and agreeing
I'm
on
so
some
glad.
things. So let's try with another one. JWST and Emiri is flying. On the horizon, we see the Ariel Space Telescope with some infrared low resolution spectrometer. But the METIS instrument on the ELT is probably the instrument that is most similar to MIRI in the foreseeable future. And because it has an integral field spectrometer and the coronagraphs and everything. Can you tell me what, in your opinion, is relevant in what all the work on calibration and modeling of the MIRI instrument? What is relevant to help us calibrate METIS observations? And what big challenge for METIS is absolutely not covered with all the beautiful work you and your colleagues have done on MIRI calibration?
Yeah, I think one of the main things is that charge migration might, of course, still happen. The detectors are different, but this might still be a problem. And I think one thing that we've learned is that it's just very important to know the properties of your detector. So if you know the properties well, you can model these effects a lot better and just remove them better than what you're doing now. Because if you just assume nothing is happening, you're wildly overestimating or underestimating your flux. So that's not great. So I think that's one of the things that if we can, from the tests beforehand and during commissioning, characterize the detectors a bit better. One thing that hopefully will not be as much of a problem is all the scattering problems that we're having. I have also been told that the GeoSnap detectors cannot have persistence. It's just solid state physics, I've been told. And I hope that they'll confirm this when they test this properly. So yeah, there are a couple of things that hopefully aren't going to be a problem. And fringing is, I think, the major one that should hopefully be less or non-existent.
Okay, and other color, not only about the detectors, but in something that is clearly a big issue for METIS that we haven't been bothered about at all.
Sorry?
No, nothing. Are there any calibration aspects or challenges in calibrating?
You mean
METIS
the fact that
instruments?
it's a ground-based instrument and there's a sky? That's not applicable to JWST. That's true.
Yeah.
Is that what you're trying to?
Well, that's a difference.
Yeah, no, it is a big difference, and I think it is going to be a big challenge. Maybe less so than for some of the shorter wavelength detectors, because or instruments, because the PSF is smaller, so you're a lot more sensitive to aberrations and changes in your atmosphere. But of course, one of the main the reason that METIS doesn't operate in exactly the same wavelength ranges as MIRI is because of the specific windows where we can actually see infrared light. So that's one limitation because of the atmosphere that we have.
Okay, so Mr. Chairman, at the point where we still agree, I think it's the point to close the discussion.
All right, thank you very much. Thank you to all examination members. I assume that there are no questions from the supervisors. Okay. Now we have plenty of time for friends, family members, colleagues. Are there any questions? Last chance. Okay, then thank you again very much for your presentation and for the discussion. Now with all members, we will move to the other room for short deliberation, and we'll come back here in a few minutes.
technical issue.
Otherwise, I can probably try this one. No, this is not. Let's move here closer a little bit. It's not such a big room, so I think it should be all right. So, ladies and gentlemen, dear colleagues, it was a real pleasure to be chair of your PhD. I really learned a lot, so thank you very much. So I will now proclaim the results of the deliberation by the examination committee appointed for granting the doctoral degree in science, astronomy, and astrophysics. Danny Gasman has presented to the faculty the PhD thesis on the topic towards resolving the planet formation in action with James Webb Telescope mid-infrared instrument. In partial fulfillment of the requirements for the PhD in science, astronomy, and astrophysics. And Danny Gasman has defended the thesis in a public session before the examination committee. The examination committee has determined that all requirements concerning the granting of the doctoral degree that are prescribed by the law and by the university regulations have been met. Therefore, on behalf of the rector of the KU Leuven, I confer upon Danny Gasman the degree of Doctor in Science, Astronomy, and Astrophysics. Before closing the session and before you can say a few words if you want, I have to read a final sentence, which is the law of the university. So by obtaining the doctoral degree, you commit yourself as a doctor to act also in the future in accordance with the basic principles of research integrity as described in the ALIA European Code of Conduct, reliability, honesty, respect, and accountability. Congratulations.
Thank you.
Danny, Dr. Gasman, congratulations. You've done a really great job, fantastic job. I believe everybody agrees. It's a pleasure for me to see you achieve this milestone today. So even if I was not deeply involved in the supervision, I've been following your work with really great admiration. It was really great to follow your progress over the years and to work with you. It was really a pleasure for me. I would like to thank and praise Yanis for the day-to-day supervision. I think you made really a great team together, and it was also a pleasure to see that. I have a small gift for you. In one of our discussions, you mentioned that one of your goals is to become a leader of your own team. And I think today you have shown that you have all what it needs to become that. I would like to see that at one day. So I had a small gift to help you on that path, but I had an issue yesterday with an Amazon delivery at the institute. We didn't find the mailbox. So I have another small gift in the meantime, and you'll get the real gift next week or when I see you. Okay?
Yes.
Congratulations.
Thank you so much. I also do I give that later? How does that?
Yeah,
work?
let's
I give that later.
continue.
Okay.
With this.
Thank you.
Thanks, Danny. Dear Danny, Dr.
Yes.
Gasman, congratulations.
Thank you.
This is a big moment for you, and I know you don't feel it yet, and it's normal, but it will come. It will dawn in you. But unfortunately, I'm afraid I have to, let's say, spoil the moment, because as you know, we have these traditional speeches, and one of them tends to be a bit longer than the second. So I just wanted you to know that, giving a PhD is a big milestone. And so even though I didn't give a PhD defense, that was because of COVID, I'm sure you can appreciate that right now this is a wonderful moment for me, but I'll do my best. Now, some of you may know that both being doctors, Danny and I, it's actually not the only thing that we share. So we also both did our bachelor's at TU Delft in aerospace engineering. And despite the separation a number of years, we even had the same teammate in one of our projects, Manish. And so I'm presuming also that some of the members in the room also knew who I'm talking about and maybe also did their projects with him. So that was a fun coincidence, let's say, when we both met. Contrary to Danny, though, I did not do a master's at TU Delft. And so because of that, I do not hold the title of ingenieur. And Danny likes to remind me from time to time that we are not the same. Okay, but that is very impressive, right? So you switch careers from engineering, then move to do a PhD in astronomy and astrophysics. And to be more specific, you informed me did not one, not two, but 3 PhDs. One was in instrumentation, another one was in astrochemistry, and a third one was putting up with my yapping. So we'll see how that third one goes. You haven't passed it yet. So one thing I learned from you, though, is that sometimes in the Netherlands, people say, doe normaal. This expression comes from the fact that a lot of people in the Netherlands don't exactly like to stand out and stand out from the crowd. And so at this point, I thought we could tally a bit your academic career until now. So you started out of school in Purmerend, and you've told us that it's quite a particular place. And you got into TU Delft, which just so happens to be one of the very highly ranked universities across the world. Then you completed a bachelor and master's degree in aerospace engineering, which is quite literally rocket science. Then you started a PhD and contributed to the operations of the biggest telescope in space, given that now it's observing also the beginning of our universe. And then, even though you don't like to brag about it, you published 6 state-of-the-art scientific papers, you got 3 travel grants, and were awarded 30 hours of expensive JWST time. And just to cap it all off, you also got a prestigious fellowship at MPIA in Heidelberg. Now, anyone with all these, lists would feel proud, but I know you well enough by now. So to me, I wanted to highlight something slightly different, and that's actually all the things that are difficult to quantify, all the parts between these achievements. And so I wanted to raise to the attention of the audience here that throughout your PhD, you prioritize your well-being by not working on the weekends and sticking to a 9-to-5 schedule. And I really cannot stress enough how important this is. In academia, it's very difficult to really stick to such a routine, and it should not be taken for granted. You also prioritize your hobbies and your time with your friends. And you also participated actively in the meetings of the junior staff, the so-called GATKIPs, which I'll leave the people in the room to explain what the acronym stands for. And then also outreach, and you also taught many bachelor ducklings, as you like to call them. But most importantly, you drew in your network actively, both professionally and also personally. And I think all your friends in the room and online are a testament to your genuine character. Beste familie van Dr. Gasman. De sterke verhaal die jullie hebben grootgebracht staat voor jullie. Misschien iets te sterk. Mogelijk heeft dat te maken met de kaas die jullie haar hebben gegeven. Danny vertelde ons hoe jullie haar vroeger al met veel inzicht verstoorde professor noemden. Vandaag heeft ze weer een stap dichter bij die positie gezet. Ze laat het er makkelijk uitzien. Danny, congratulations again. I'm wishing you every success in your life, happiness, and most importantly, lots and lots of good food. And I'll start that with my little present, which I guess I'll give now. Oops, other way. There you go. And I'll give you the congratulations.
So I guess it's up to me now. I hate speeches, so I will not give one, but I will give gifts, because I do like giving gifts. So for Denis, I hope you enjoy. And I'm just going to give you the other things that are in there, and you can open them.
At the last bag.
Yeah, well, there's stuff in there that's beautifully wrapped in very thematic paper, but the inside is what counts. So yeah. And with that, I would like everyone to go to the other room and have some drinks and food. So.
Enjoy your day, Dani. Bye.
Thanks, Inga. Thanks, David.
Congratulations again.
All the best.